Next, let's talk about what happens to those reactants as they go through a process. So the first way we might define that is fractional conversion. And the point is that reactions rarely go to completion. There are many reasons for that. One is they may have an equilibrium point. Another may be that we just simply stop the reaction by some procedure that we do before it has a chance to get to completion. So if we want to know how close it gets to completion, one of the things that we can use is fractional conversion. Now, fractional conversion is pretty much what it sounds like. It's the moles that actually react compared to the moles that were fed into the process. So how many moles of molecule A actually converted, okay, or reacted, okay? So if we look at this little example here we have a feed that's 75 moles SO2, 25 moles O2. So in this case, I have excess SO2 and I'm limiting in O2. We've looked at this in a previous video. In this case, I know that when I look at what comes out of this reactor, I ended up with 35 moles of SO2 left over and 5 moles of O2 and created 40 moles of SO3. So if I know what's coming in and out, I can calculate the fractional conversion. But it's going to be a different value for each compound. So for SO2, I came in with 75 and left with 35. Divide by how much was fed, and I ended up with 0.53 as the fractional conversion. A little bit more than half of it reacted. For my O2, 25 came in, 5 left. Divide by how much was fed, and 80% was converted. So we can see that, okay, this was the one that was in excess, the fractional conversion is lower. The one that was limiting, the fractional conversion will be higher. So that's going to be kind of the way that the numbers should work out. Okay? The only time that these two fractions will be the same is if you happen to have been fed in stoichiometric proportion. Now, this is not the only way that we can talk about how much reacts, but it is a very common one. Now, I do want to make just a couple of comments that will help you with doing these next couple of sections, and actually through the rest of the book in some regards. First of all, anytime you're working with reactions, it is going to be much easier for you if you work in moles rather than mass. You can do mass, but mass doesn't balance. Well, I mean, it balances, but mass is hard to keep track of with reactions. Moles, they don't actually balance, but they're easy to keep track of because I know that SO2 and an O2 combined, so the number of O molecules stay the same throughout. So it's just going to be easier. Work with moles. Anytime you see a reaction, just think, I should convert all of my masses into moles. Now, another thing that you need to note is that in this textbook, they use X for fractions for mass and Y for fractions for moles in this chapter. When they move later in the book, it's going to change. If you move to another textbook or another web resource or whatever, the notation will not be universal. So don't expect that every time you see X, that's obviously a mass fraction, or Y is obviously a mole fraction, because that simply is not true. Okay? It's just a convenience thing for this chapter. Now, I said there were other ways of talking about how much reacts. The other very common one is extent of reaction. Now, we use the symbol C, or I call it squiggle, okay, to define extent of reaction. Now, if you use nu, I know it looks like a V, but it's the Greek letter nu, lowercase nu. If you let that be the stoichiometric coefficient for the component in your reaction, and you say, okay, whatever the stoichiometric coefficient is, I'm going to say if it's a product, it's positive. If it's a reactant, it's negative. And we're also going to then start dealing with things that are inert. Okay, things that do not participate in the reaction. So maybe I have SO2 and O2 reacting to make SO3, but instead of bringing in pure O2, which is expensive, I bring in air. And so there's a lot of nitrogen, and it's not participating in the reaction, it's just hanging out. And so for those, I'm going to call 0 this beta value. And so this beta, which is either the stoichiometric coefficient with a positive or negative, depending on whether it's product or reactant, or 0 if it's inert, when I use that, what I can do is I can do a mole balance on each species. The number of moles that come in plus the amount that react. So the stoichiometric coefficient with a sign, okay, times this excess or extent of reaction, the squiggle, okay, that will tell me how many moles I'm going to have coming out of my reactor. Now, one of the things that's very nice about this is extent of reaction is going to be the same for every component. It just depends on the way I write the reaction. Which is to say, so I had 2 SO2 plus O2 makes 2 SO3. That will give me one set of expressions. If I chose to write it as SO2 plus 1/2 O2 makes SO3, I would get a different expression here. So the extent of reaction is going to depend on how I write the chemical reaction. But it will be the same value for all the components within that reaction. Fractional conversion, different. Every component has a different fractional conversion. So let's look at a quick example here. For this reaction, if I have 2 SO2 plus O2 plus 2 SO3, then the expressions that I would write for SO2, O2, and SO3 are simply going to be the initial number of moles of each of those. For SO2, it's minus 2 squiggle, okay? So 2 get consumed, that's why minus. For O2, minus squiggle because 1 gets consumed. And for SO3, plus squiggle because none get consumed. If I had had some nitrogen in the system, then I would expect that the number of moles of nitrogen at the beginning would be the same as the number of moles of nitrogen at the end. So it would be plus 0 squiggle. Okay? So if we look at that reaction that we just had that was 75 moles SO2 and 25 moles O2, what I would find is that I have these as my expressions for each of the different compounds. So we're going to pause there. We're going to come back and do another more in-depth example in the next video.